Once that goes, perfect. All right. So I'm going to record this for a later date. Thanks for whoever put that in the chat. I almost forgot. So Siemens, we have a lot of resources and we're kind of vast on the information that we have. And we actually did a nice thing. We put it all kind of in one place. And what that is that's usasiemens.com /CNC for you. And there's a lot of information there. There's a spots to join the webinar. There's spots to sign up for trainings, training classes, also pointing us to our YouTube page. So this is a really good website to where you can really find some information about Siemens as a whole. So like I said, we have in-person and online trainings. There's a tab when you get there, when you go to trainings, you can actually sign up for in-person trainings now. We have the whole schedule for the whole year for service classes, for in-person 5-axis classes, for online classes. Online, interesting enough, we're running an online class every single month. So we're going to go through 3 waves of our level 1 and level 2 classes. Really kind of get your feet wet of how to either use shop turn or shop mill or G-code programming. So it's really kind of huge if you really wanted to kind of understand how to program Siemens control, whether it be conversational or whether it be G-code. So it's really, really powerful. And we have that every month going on. To dive in a little deeper, the in-person classes, like I said, when we go to a higher level, like a level 3, and we talk about 5-axis and we talk about a little bit of probing in there, we talk a little bit about everything in there, we tend to have those in person. That way we can kind of go on a 5-axis machine, understand what cycle 800 is, understand what Traore is, understand these technology cycles, so that we can kind of go a little more hands-on feel when we go to that. Which brings us to kind of a social media platform that we have. We are heavily on YouTube. We use our YouTube channel is called Mr. CNC. We do promotional videos, how-to videos, YouTube lives. We tend to try to run a webinar every other month, and in between those, we try to do a YouTube live. So we're really trying to promote those. So when we get done with this webinar, we will post it on our YouTube channel so that you can go back and look at it there. And it's kind of a whole, a housing for all our videos and how-tos. Another cool piece that's on our CNC for you is virtual product expert. So let's say you had a question about Siemens, about shop mill or cycle 800 or Traore. How do you program 5-axis and you don't know about it, or you have a SINUMERIK control and you don't know about it? You can sign up when you go to the VPE on our CNC for you. Sign up. You'll get an instant meeting request, and then you'll go right to a meeting with one of our virtual product experts, and we'll answer you, go through your question, go through maybe even a simulation of your question on a demo machine on our piece of software that we have, either be Sinutrain or My Virtual Machine. So we have a wide array of how we can answer your question. So being a probing topic, and what Chris has done in the past is he's made a really good video about how you probe on a sinumerik control. So basically, Chris is Mr. CNC. He's really built up the YouTube channel, and he has over 111 videos right now of hour-plus content on a sinumerik control. Here we have the probing video that he did a while back. He did that in 2018, where he went through pretty much all our probing cycles that are standard on sinumerik. So how to utilize that. And then when I came on board, I wanted to kind of take that webinar and go to the next level. What I did there is I went through probing measure, cut, measure. So we took our standard cycles, and then how do you actually measure on the machine, and then how do you update your code or your tooling to give you the best part on the machine. And then in thinking of this, I always had AAT3 in the back of my mind. And what the reason why is because that goes like the next step, how you're going to measure something on there. So this is kind of more manual. This is all you have to either use our cycles to update your tools, and then you got to write it to a report, and it all has to be a report manually written into your programs. So then I always wanted to see, if AAT 3D would like to join and give us that next level where it's you do the same type of thing, but you're going to have a report spit out at the end of it. And I think that's one of the things and one of the aspects of having AAT 3D with your SINUMERIK control as an aspect. So really powerful. Um, so just going through our profile really quick so that I don't take too much of AAT 3D's time. We have a couple different controls that we can actually put AAT 3D software on. We have 828 that we can put it on, 840D, and then the newest control is going to be SINUMERIK 1. So this is all can be put on all our controls. What we mean when we are talking about probing standard on our machine, we definitely have jog programming and automatic programming. So we have both these functions. These are the things that we talked about in the 2 webinars before that I put links in the description, and I'll put that in when we post this on YouTube. But these are kind of the modes that we take on standard probing on our machine. These are some of the standard probing cycles that we utilize on our machine and how we can utilize these standard cycles to do measure, cut, measure. And just to kind of, when you need these cycles, this is the kind of option that you're going to need on your machine just to kind of plug in. This is what you actually have to have if you are going to run these types of cycles on your machine, just to kind of FYI. Usually you're going to have this cycle if you're going to go to the next level, such as AAT 3D with NC Caps. What I did in the measure cut measure webinar, just to kind of let you know, I went through how you probe and use automatic probing with the first op and second op operations. How do you do in-process measuring a feature? How do you update a tool offset with a probe feature? How do you use measure results? And then how do you use the write command to write your report that you wanted to have from that? And then I went through a live demo. That's what I did when I did the measure cut measure. The reason why I kept this slide for this webinar and why I wanted to kind of go in this is the next level that AAT3 brings to the table to all these aspects of this type of webinars. This is all really someone's focusing on this, and they have to do all the work to do this. And when you go to someone like AAT3D, when they hook up to your machine, they make this process a lot more streamlined, a lot more faster, and coming with a lot more data. So without further ado, I'm going to introduce Chris and John. They're on the line, and they're going to start to become the presenter now and take over. So I'm going to stop presenting, and they're going to unmute, right?
Yes, we are here.
Perfect. And then I'm going to change you into presenter mode.
Okay, so I'm going to go ahead and open up our PowerPoint presentation here.
Perfect. So Chris is from AAT3D, and so is John. And I don't know if you can do a brief introduction of who you are and how long you've been with AAT3D, and then we can go with your presentation.
Awesome. So I'll go ahead and start. And when we switch over to Chris, I'll let him introduce himself and give his timeline as well. My name is John Ripperdan. I am a former CNC programmer. I've worked for AAT for about a year, or a little over a year now. And my background is mostly in production and R&D programs. So I was both an operator, then I became a programmer, and really focused hard on the programming and how to automate a lot of processes. So coming to AAT3D was a really nice move for me because it got to take me to the next level as well on the whole probing on machine, getting reports, and really hitting home with a lot of the production that I normally would do. So let's go ahead and get into our presentation, and then when we switch over, we'll have Chris go ahead and announce who he is and his background as well. So first off, thank you for having us on the webinar. I appreciate that. We're very excited to kind of give you guys an overview of cut, measure, cut cycles and give you a little bit of breakdown as far as what to expect, when to decide if you're going to do a cut, measure, cut, and kind of educate the viewers a little bit on what is going to be expected or needed to kind of perform this type of action. Okay, so with cut, measure, cut applications, basically, let's start with the beginning. When do you use a cut, measure, cut application? So there's a lot of instances when you are doing some sort of a part run or you're trying to manufacture some sort of element or process, and you have to decide, okay, do I need to use a cut, measure, cut cycle on this, or would it be beneficial? So some things that would be beneficial to be using a cut, measure, cut cycle on are going to be something like tight tolerance features, hard to machine features, maintain profile consistencies, and reduce setup time. Now, when we talk about these, we're going to go down and go into more bullet points on all of these, but the biggest takeaway here is also that last one, reduce setup time. If you know you can do a cut, measure, cut cycle, keep in back of mind a lot of everything that I'm going to tell you, you can pre-plan a lot of this information to make sure you get a first time right part. So let's go ahead and go to the next slide and we'll talk about the first thing on the list. So first thing is going to be tight tolerance features. Now, what would constitute as a tight tolerance feature? So most people, when they think of this, they're going to think, okay, well, I have a datum that's going to be the relationship between another positional call out on my print. That datum needs to be put in perfectly or be held to a certain size, position, so on and so forth, dependent on other datums that may be on your print. These tight tolerance features, you really have to make sure you nail them. So something like if you have a least max condition or a maximum max material condition, you may want to go ahead and recut the size of it. So that would require you to do like a cut probe. So that way you can make sure you have the correct size. So that way you get the most bonus tolerance for achieving your desired outcome. Size tolerances go right into that, obviously, like we're just talking about with trying to achieve that desired outcome. And then you have profile accuracy to datums and positional tolerance to a feature size. These can all be really tied into that because if you already know ahead of time that you can do a cut, measure, cut cycle, you can plan ahead of time with your putting in your datum, establishing it perfectly, and then cutting and little by little dialing in that feature in retrospect to that. Moving on, we have hard to machine features. Now, hard to machine features, these can classify as a lot of things. Notice that I do have a list on the left-hand side of some features that could be considered hard to machine, but I also have the image to my right. Now, most would see that and go, okay, this is going to be something that I'm going to do some sort of a contour path to, whether it's going to be a 3D volume mill or tricotal tool path to go ahead and whittle all that down and leave a scallop step over that I can come in and establish with a hog nose or a ball mill, right? What if you could actually use your probe and measure the actual profile of everything and correlate that to using another software and then actually making adjustments to make those types of features very, very accurate? Your probe on your machine can actually accomplish this as long as you know that you can do a cut, measure, cut cycle. As well as establishing, when we talk about concentric bores, for example, the top one, I know a lot of people out there do a lot of porting applications. When we talk about ports, typically you have 2 to 3 concentric features in that feature that you want to make sure that you're using the same tool to establish to maintain your sizes. That would allow you to do a cut, measure, cut. So you can cut one feature and dial in that cutter comp and then continue on like you normally would. Also, I do want to touch base on the symmetrical features because notice the image that I have here as well. You'll see that a lot of these are semi-symmetrical. With a cut, measure, cut cycle, you can measure one of them, make an adjustment, and then be able to establish all of those features with the same relationship. The next one that we're going to talk about is going to be profile consistency. Now, you'll notice here that I have a picture of a helicopter blade in the top of the helicopter. The reason being is because a lot of people out there are aware that to achieve lift, you need to have a good beginning edge and a good trailing edge to establish lift on a wing. That is a profile type call out on most prints that using a probing software or cut, measure, cut cycle will allow you to verify that you're cutting your trailing edge and your leading edge appropriately and symmetrical to themselves. You can also use a cut, measure, cut cycle to verify your contour profiles or even splines, because splines are something that's going to be very difficult to cut accurately that if you were to try to probe, let's say on a CAN cycle, you would not be able to do. But if you use a higher level of camming software for probing, you can then take that and actually correct your tooling for this. Now, keep in mind that these types of features, when we're talking about them, these are very hard to machine features. So utilizing a cut, measure, cut cycle is something that's going to be very, very impactful and very beneficial to establish perfect sizes every time, and even to contour and change your tools on the fly. Because you may have something like this that takes a very, very long time to cut. So you may want to build in the cycles to really verify your tooling while you're doing it. Cut, measure, cut cycles can help you with this. Moving on to the last one, which is actually one of the ones that are probably the most important when you're talking about cut, measure, cut, is going to be reduced setup time. Now, why would you use a cut, measure, cut cycle to reduce your setup time? You would use that to, one, if you want to find your part every time. Let's say you have a fixture or you have a tombstone or pallet system that maybe as it gets put in there isn't as refined as you thought it was. Or maybe you have some fixtures or some vices that are a little worn out and you're just using like a bump stop or a 3-2-1 or something to really hold on to this part. You may want to go ahead and probe it to find that part. You could typically do this on most CAN cycles, especially like the Siemens ones that they were talking about at the beginning. Or you could do this and build this into your functionality of your program, so that way you can find that part location and probe it, right? And then that way you can have it. So let's say you're going to remove extra stock to make it uniform. You could use that and use a cut, measure, cut to verify that you have the part location. And also, so you can use your probe to set the 6 degrees of freedom work offset back to it. So that way when you go to do a cut or a cut, measure, cut, you know you're nice and accurate like you should be. Also, one other benefit of doing this and reducing your setup time is the simple fact that you can literally use a cut, measure, cut cycle to automate all of your cutter comp dilation. So for example, if you were to start at the beginning of your program and zero out all your cutter comps, if you know you're going to use cut, measure, cut cycles, you can go ahead and build that into your process. So each cut that you take, you can go probe and verify. This may seem a little bit redundant, but when we talk about a setup, the most redundant part about a setup is usually the operator's choice or the programmer's choice when setting this up. If this is a repeat job, some people of different, we'll call them educational hierarchies, may not understand some of the intricacies of like a 5-axis program setup versus a 3-axis program setup when you go ahead and you dump something over 90 degrees and it does more than just affect one of your variables. By baking in cut, measure, cut cycles and automating a lot of that process, even though it seems redundant to go ahead and do this for every single cutter path, you could essentially do this and verify all the locations, your cutter comp right from the beginning. So that way you get a first time right, or if you're cutting a fixture or a mold, you can get that done the first time correctly, which then you could then take out some of the probing cycles later, and that would help you with reducing the setup time that it actually takes to make and perform. Next slide we have here is how to start. So we talked a lot about, okay, what applications would you use the cut, measure, cut on? How do you start? What do you do? That's a good question that a lot of people out there will go, well, I have an idea of how I want to do a cut, measure, cut, but at what point should I really interject this? There really isn't a right or wrong time to interject with a cut, measure, cut cycle. However, knowing is half the battle. First things first, if you really want to go at the root of it, look at your print and review it. Some of the things that you could be looking for when you're looking at a print is what tolerances do you have? You may not want to do a cut, measure, cut for your entire program, and that's okay. You may not need to. You may have a couple of datums, a couple of positions that maybe they have a tight tolerance like a thou, 2 thou, or a couple of tenths even, right? By knowing ahead of time that you have these features that you need to establish, you could kind of build yourself a template or an outline saying, I know I need to use a particular tool to establish said feature. And by doing so, I know that I can meet this print requirement for that tolerancing. Now, another step forward is going to be, is this a production run or is this an R&D type part, right? When we talk about production and R&D, there's a lot of things that could go into this. A production run could be anywhere between, let's say, 10 parts to thousands upon thousands of parts. With that in mind, you're going to want to have a robust system to make sure that you have repeatable results. You may dial in your cutter comps. You may dial in everything to where you have your minutes of every tool dialed in, so you can just swap them out in a timer automatically with sister tooling. You may not need probing. However, you may have a couple of features on there that even though you have your tools dialed in, they may be critical features that you want to verify every single time. With doing that, you can use a cut, measure, cut cycle, so that way you can automate that, and you know those critical features are always going to be good. Now, when we talk about R&D, R&D is a little bit different. It's R&D for a reason. It may be for a discovering if a part's going to work, testing out a theory, testing machinability. Cut, measure, cut cycles can really be utilized in that aspect because you can bake every single tool path with a cut, measure, cut, so you can verify that your R&D project is going just as smooth as you think or it wouldn't. Now, obviously, when we're talking about production and R&D and inspection, you may have an in-process inspection, right? So keep that in mind with the cut, measure, cut. Are you going to have certain features that need to be checked every single part or every couple of parts? If you do, you can bake that into your cut, measure, cut cycle and logic to allow for you to go ahead and inspect the part while you're cutting and adjust the compositions, right? So you can double up and kind of double dip a little bit on how accurate is your feature actually going to be, as well as go ahead and get that data that you need for your end report for in-process inspection. Last but not least, what we're going to talk about is you need to know how accurate your machine is and how accurate your probe is. Funny enough, they do correlate, and you will see, and you could use your probe to actually verify your machine accuracy. So in the next slide, let's go ahead and talk about what we have with the probes. Now, understanding machine tool probes is pretty simple. Really, you have a probe in your machine, and there are really two types out there. You have a kinematic, which is going to be a physical trigger system, or you have a strain gauge probe. Strain gauge probe is going to be more like an electronic signal, which is going to be very similar to your CMM. Notice the topic of the discussion is the turning your CNC into a CMM, right? So using the strain gauge probe is usually a little bit more accurate. However, even with a mechanical trigger from a kinematic probe, such as a Renishaw RMP 40 or 60 or any Bloom or Marpost probe, those are still just as accurate. However, just need to be aware of the fact that it's a mechanical trigger. So if you are not measuring perpendicular or normal to, you will get a slight error. So you really want to go ahead and calibrate those types of probes with a vector calibration, we call it. So that way you can touch at any point in time with that ball and get an accurate reading. Whereas with a strain gauge probe, you don't necessarily need to do this. But at the end of the day, if you're using a software that's a little bit more involved and you're not just using a ring gauge to calibrate your probes, you can actually take a lot of that error out and utilize either probe just as well as you would the strain gauge probe, which would be considered usually the higher end probe. Now that we know, okay, this is how our actual probe is going to work, or how they interact, or how accurate they could or could not be, at that point, you can take that information and you can apply this to your machine. Now, we all know that there are many machine builders out there. Some machines are retrofitted with other controllers, such as Siemens, Heidenheim, Fanuc, whatever the case may be. And also, all machine builders use all kinds of different machine controls. However, with your probe, you can actually verify and check how accurate your machine is. You can check your kinematics. You can use something like a Tetra check, like we have here in the picture, and you can actually probe that at different locations. And they have an algorithm that'll tell you the health of your machine. That's something that's definitely very beneficial with utilizing your probe. And like I said at the beginning, when you're trying to start this process and you want to trust, can I do a cut, measure, cut cycle? First thing you need to be able to do is trust your probe and your machine. By trusting your probe and understanding and having the knowledge of what probe you have and how accurate it is, you can then verify the machine accuracy as well. So that way you know exactly what you can achieve. You may not be able to do a proper cut, measure, cut cycle and hold a foul tolerance if your machine has a little bit of wear, right? However, if you're aware of this, you may be able to compensate for that in some other manner. Moving right along, we have the setting up a cut, measure, cut. Now, when we talk about setting up a cut, measure, cut, there's a lot of different aspects that can go into this. You really need to think of what the tool is that you're using to establish a feature. You need to think of the process that really goes along with this. This may be something that's very simple to do. It may just be something where you're interpolating a hole and you'd like to just open or close that composition as you're going. Or let's say you're going to do several profile side paths, right? Understanding your tool path is going to help you with probing it and knowing, okay, how am I going to comp and or adjust this tool appropriately? One other thing is, if you know you're going to do a cut, measure, cut cycle, and the how-to portion of this is you're going to identify the tooling that you're going to be using to establish said feature that you think you need to cut, measure, cut. That's going to be a huge step in the right direction for you, because if you are limiting your tooling to cut, measure, cut cycles, that means you can then eliminate variables. Let's be honest here, when we talk about setups, how many times do you go through a process and check every single tool and the result to match the CAD? Let's be honest, most people don't. They'll cut a part all the way through and they'll expect it, and then they'll make their comp adjustments and their work offset adjustments. However, if you know going into it that I have the ability to do a cut, measure, cut because I can trust my probe and I can trust my machine kinematics, that can allow you to limit certain tooling to manage it in a way that allows you to do on-the-fly cut adjustments while doing and manufacturing that part. Another thing to keep in mind is you may want to automate this. You may want to do a do-while loop where you cut one feature, let's say a profile, and you measure it and you discover that, okay, this is out by 5/10. I need to remove another 5/10. You can automate it to adjust that cutter count by the 5/10, and then rerun it again, and then probe again to verify your action. Or you can cut a feature, measure it, and decide, okay, maybe I just want to update this for the next part run or the next cut. And you can build all this in with some logic statements. Moving right along, here's the diagram that kind of gives you an example of what a cut, measure, cut loop would really look at or work with. So you're going to notice in the center, we have an image of a CNC machine. Now, we're going to use just a generic image here. This could be any of your machines, right? This could be any of your controllers. This could be anything that CappsNC is installed on, or any other probing software, or even canned routines. Notice that the first operation is usually going to be some sort of a cut. The next operation is you're going to call a probing routine, whether this is going to be a can cycle, or maybe this will be something that goes along the lines of what us at AAT3D provide, just CappsNC, which allows you to call a dedicated probing cycle or program that you've made in our software, or even just a lot of individual probing calls, right? At that point, you're going to go ahead and measure said feature. And then you need to decide if you're going to recut or update for the next cut, at which point you can go back into the CNC program, or if you want to automate that process and then go ahead and get that dialed in and then go back to the CNC machine. Those are options. Now, all these options do potentially take time. However, getting a part right or maintaining quality of a part usually can lead to a lot less headache moving forward, especially so that way you don't have recalls or have to do some sort of assortment because maybe a tool wore prematurely and you didn't automate the process. Moving on from here, we have an example of NC program with cut, measure, cut. Now, these are some Siemens cycles that we put together. Notice on the left-hand side, we have a main program. Now, at the main program, you're going to see that we just established a work offset in the top left. Moving on, you see that we have some sort of declarations. So you'll see that we are setting an R value, and we're using identifiers here, and we're essentially setting up a loop. And now this loop is going to be something that, if you're using canned routines, will allow you to just keep kind of living and cycling through this until you've established an R variable that allows you to move. However, if you're using something from CappsNC, our product, you'll notice that you can go ahead and have your cutting path call a program, which will be the start of the sub and end of the sub here, that then allows you to run a full dedicated program just for probing. And you will notice in the right-hand side of end of sub in the red box that we have a work offset feedback where we have updated a work offset and a rotational work offset. And at the very end, we've set an R value to 50. So you'll notice that that red box ties to our red box on the left-hand side from our main program that says, if R140 is greater than 1, go to the start loop. So at that point, you have now an automated process that'll keep going until your R value is set to 1, which will then end your repetition. Now, with that being said, this is just one example of how you could do a cut, measure, cut cycle. And this is how to kind of interject that in your code while making a process. Unfortunately, sometimes when you're doing a cut, measure, cut, you may have to do a little bit of manual work to get this work running properly, or you can use our software and measure this at the end and make it completely automated. Now, at this point, I'm going to go ahead and I'm going to turn the presentation over to my senior applications engineer, Chris Affer, and let him introduce himself.
Thanks, John. So as John said, my name is Chris Affer, a senior applications engineer here at AAT3D. I've been with the company for over 20 years, and I've been in metrology for over 30. So the way we're going to start, or what I'm going to talk about is, so John brought up a lot of good points with using cut, measure, cut. Dan also talked about a lot of the CAN cycles that the Siemens controller uses or includes. So, but what if you have situations that fall outside of the standard range, right? So we're all familiar with probing on machines. Probing on machines is not a new technology. However, bringing the power and the control that you get from a true metrology software like you would have on your CMM is new within the last, let's say, 10 to 15 years. So what's the difference? So when you look at a CAN cycle or a hand-coded program that uses, let's say, Renishaw macros or something like that, you're limited to what those macros are able to do. For example, if you want to probe a hole, for example, you can probe 4 points and get a hole size, location, things like that. But what if you wanted to interrogate that feature more? What if you wanted to look at the form of that feature? What if you wanted to make decisions off of that feature? What if it was extremely tight or something like that? by using a metrology software on your machine, as opposed to using a probing software or canned routines, you have a lot more flexibility. You have all the flexibility that you would have at your CMM. Okay? So a couple of points that we want to hit here is one of the differences between a standard probing software and our metrology software is that we have a real-time connection to the machine. So we have a PC directly connected to the machine. In this case, let's say an 840D controller. We are connected through the OPC interface, so we have a live connection to the machine. While the program is running and the probe is probing on the machine, the points are being fed back to the PC in real time, and then the software takes the points and plugs them into the different features that are needed and how the program was done. What this allows us to do is to interrogate the features that are being probed very deeply. Right, so you could do a 50-point circle, for example, if you needed to. Or what if you learn from your quality department that instead of just getting a 4-point circle and looking at the diameter, maybe the best thing to do is to use a max inscribed or a min circumscribed calculation to calculate that diameter based on the type of feature that it is. The metrology software is going to give you that tool to be able to do that analysis real time while the program is running on the machine. Along with that, we also have the ability to do some calculations in the software and then feed information back to the controller real time. So you can feed back into R variables, have your cutting cycle analyze those R variables, make decisions based on those results. You can do work offset updating, you can do tool offset updating. All this can be done live while the program is running on the machine, either separate from the cutting cycle or inside of the cutting cycle in a cut, measure, cut type of environment. All of the data that you get from the machine is stored and managed in the PC. So we're not managing anything through our variables. We're not managing massive amounts of data through our variables or anything like that. We just have the capability of doing all the computations and calculations on a separate PC rather than doing it in the HMI. Along with this, we have advanced alignment capabilities. So I know Dan showed us some of the conversational screens that they have for probing in the Siemens controller. And for most situations, those are great. They work very well. But what if you had a situation where you have a part with a very complex surface or complex geometry on it, and you can't use a traditional 3-to-1 alignment or a hole find routine or something like that. You can't use those type of macros to set up your part. But you can use our software, the CappsNC software by AT3D, to probe a myriad of features on the part and use that information to generate what we like to call advanced alignments. Okay, so from those advanced alignments, the good thing about it is that an advanced alignment is going to create the same 6 degree of freedom transformation that a standard alignment would create. Okay, it's just going to do it using different types of features. Okay, so once that 6 degree of freedom transformation has been created in the software, it can be fed back into the control, into the work offset, and utilized in the way that the machine is capable of doing. So if you can only apply translations, let's say it's just a 3-axis mill, then you just feed back translations. If you want to feed back all 6 degree of freedom because you can maybe create a work frame that uses Triori and that works in your situation, that's fine too. You can create that work offset, that 6 degree of freedom transformation in caps, feed it back into a work offset, and then activate Cycle 800 on that work offset. So there's many different options that you have for this, but what we want to really kind of focus on here is the fact that we're able to calculate some more advanced alignments that you may not have the ability to do in a standard system. Okay? And then finally, once we have all this information, if we want to, we can create a GD&T report that is very similar to what you would get off of your CMM, right in line with what you would get off your CMM. Okay, so what does our programming environment look like? So if anybody on the webinar here is familiar with any CMM software, it's going to be very, very similar to what you have in a standard CMM software. So we have a graphics window. So it does have a CAM programming environment. Okay, we can model as little or as much of the machine as needed. We can also model the probe. You can have different probes. So if you have more than one probe in your machine, you can actually model each individual probe, switch between the probes in cycle, just do a tool change, and probe all the different features that you need. On top of that, we also have full path generation. automatic geometry path generation. So if you want to measure a circle, for example, and you say, you know what, this hole is important to me. I think I need to measure, I don't know, 37 points in this hole. You know, you simply just identify the number of points that you want to measure. The system generates the path for you, and all you're doing is programming this in this CAM environment. All of the paths that are being recorded are being stored in our tree. You can see it on the far right side of this image. And then once the program is completed, you can simulate it. We have collision avoidance built into the software, so you can apply the collision avoidance while generating the probing paths, or you can do it post before you run the code through the post, so that you can get a visual simulation and collision check before you run it on your machine. Okay, once you're done and you're all happy with the simulation, you can then create G code right from our software. Just kind of a 30,000 foot view on that. The G code that's generated from our software is a macro based G code. So it calls basically a bunch of sub macros to do movement and manage all the point data coming from the machine. Okay. Complex geometry measurement can be managed based on CAD surface contour. So if you have a part that has complex geometry on it, you can generate your measurement paths using our software on that complex geometry. And just like a CMM, all of the probing paths will be generated such that they measure the surface normal. In other words, the vector information is pulled from the CAD model, and all of the probing paths are generated such that the touch and the movement of the machine will be vector normal to the surface. So that kind of, once again, brings you into that CMM environment, that metrology environment, so that you're getting true measurement just like you would get off of your CMM. As I said before, we have a real-time data I/O interface to the machine. So there is a window connected while the program is running. While the program is running on the machine, we have constant feedback going to the software. And that's the point where we could do analysis, make decisions, and feed information back. So it is a two-way street. So we can receive information from the machine. We can also pass information and set parameters from the software back into the machine. Once again, real-time work and tool offset capabilities. So the ability to go in and create a work offset and do that full 60-degree freedom transformation feedback is very advantageous. Some examples that I can give with that is if you look at like a large-scale trim and drill machine, for example, where you have a very large fixture. Let's say you have a wing skin for a commercial aircraft or something like that. You might have a fixture that has tooling balls on it, and you can use the software, you can use the CAP software to generate a probing cycle on those three spheres, use an advanced alignment that we call MGP to align those spheres, update a work offset based on those values, load the part in, probe it again in that work offset, create a secondary update, and then feed that update back into, let's say, for example, the fine of the work offset. So you're not only are you roughly locating on the fixture, but now you're also fine locating on your part, and that fine location of the part may very well include some probing on some complex geometry, right? So all of that built into the software, and the fact that we can calculate all of these different alignments and things like that can really bring a level of enhancement or advancement to the machine. Okay, so yeah, and then like I said, advanced alignment capabilities. So in following in that theme, this is just an example of one of the advanced alignments that we have. So in our software, in the CappsNC software, we have a 3D best fit. We call it 3D best fit, or a best fit alignment type scenario. So a best fit alignment scenario is going to say, okay, you know what? I'm going to throw a bunch of features at this alignment, and I want the software to kind of calculate exactly the best fit that it can throughout the data. So it all works off of RMS. So you throw all the data at it, and the software says, okay, I'm going to calculate the best fit that I can through here. And it looks at the average error of all the features and tries to kind of even it out the best it can. Okay. We can align to nominal or CAD data. So if you have a set of nominals clearly defined, let's say by a customer, whether that customer is internal or external, you can align the actual data probed from the machine to that nominal data and come up with the best fit. If that's not needed, you can measure features and then drop them right on the CAD and have the software mathematically iterate that. So the software is going to take the actual data, drop it on the CAD and say, okay, this is the RMS error that I get. Okay, well, along with that, you would set a tolerance and a number of iterations. and the software is going to say, okay, this is what I got compared to the tolerance. If it's not within that tolerance, then the software is going to say, okay, I'm going to try this again. And it's going to keep trying until one of three things happen. Either A, it meets the tolerance, B, it meets the number of iterations, or it gets to a point where you're proverbially moving deck chairs on the Titanic. In other words, you're just shifting small amounts of air around. Best fits really kind of converge to a point, and it's really not going to get any better as it goes. So once you get to that point, you can then analyze the data, look at the best fit, and decide whether or not you want to accept it and allow to go from there. On top of that, we also have the ability to apply constraints to the system. So each individual feature that's selected, you can see it there on the left of the small picture, you can apply direct constraints to each feature. So for example, you could say, okay, I want this feature to control only X, that feature to control X and Y, this feature, and all of these features together to control Z. So you have individual feature level constraints that you can apply to manage the fit, or you can have the system generate it, and then you can decide over on the left side of the dialog there to say, okay, you know what, I don't need to feed back rotation about X, for example, and then recalculate it and have the system figure out exactly, the best way to do it. So all of this really is used to align a part that is, let's say, a non-traditional type of setup. And once again, the result is that 6-degree of freedom, well, up to 6-degree of freedom transformation that I can feed back to my control, update a work offset, and then continue on my way. So what can we do with this data? Well, after we get the data, we get it on the part. A lot of times people ask us, well, okay, what if I don't want to just probe at the end? Well, that's fine. You can use the probing information or the probing data for a lot of different things. For example, you can use it to do first article inspection, right? So I know that oftentimes in the manufacturing environment, one of the bottlenecks, in fact, I used to be a CMM operator, so I used to be on the other side of this, is first article inspection. So let's say you load a new part on a machine, you set it up, you run your first couple of parts, and now you got to send your part off to CMM to get that first article buy off. Well, what do you do in that situation? Well, let's say that the backup in the CMM room is 12 hours. Well, you're not going to let the machine sit for 12 hours while you wait for that part to come back from CMM. So what you're going to do is you're going to do some hand checks, you're going to do some key checks, you're going to check some features that you're confident that if those features are good, that you can run the part. However, you are still, quote unquote, running at risk at that point, right? You're not running blind, but you're running at a little bit of risk. So what a lot of our customers do is they'll generate a program to measure those key features and maybe a couple more features, and features that they know that if all these features relate together and everything looks good, then I can trust that my setup is good. So essentially what you're doing there is you're running at less risk, right? So you pull the part out, you still send it to CMM, you still get that first article inspection report. However, you now can run parts while you're waiting for that first article inspection report to come back, and you're running at way less risk. And that is going to help you to prevent a lot of downtime or potential downtime on your machine for part setup. So some of the features that we have built into the software here is feature construction. So like most metrology softwares, if I need to measure 2 concentric bores, create a cylinder out of them, I can probe one as a circle, come around to the other side of the part, probe that feature. So let's say it's not possible to truly measure them as a cylinder. So I would probe one side as a circle, probe another side as a circle, and now I could construct that feature as a cylinder from those 2 measured circles, and actually get the GD&T that my print is asking for. So we have capability of doing that. Collision avoidance, as I said before. So while we're programming, we have collision avoidance that will ensure that the model of our probe and the model of our machine does not unexpectedly encounter the model of our part. As you can see from the picture here, we have CMM style reports. So pretty much similar reports that you get off of your CMM, you can get right directly off of your machine. On top of that, you can see in the picture of the report there, we have little flags. We call them templates, little flags attached to the CAD model there. Those can be set up in such a way that they can be color coded. So if you have a key set of features that you need to measure, and so let's say you're making, a component for a plastic ejection mold, and you go in, you machine that part of the mold, and then you probe 10 or 20 points on it, and then you can set up a color map. So from the operator's perspective, all they do is they look at the screen. If all the dots show up green on the part, they know the part's good. Part can get pulled out of the machine. If it still needs to go to CMM, it can go to CMM. But once again, they're confident that their process or their step of that process is complete, and they can move that part on to its, let's call it, next phase of life. So you can use the reporting system as, kind of like a detailed report, or you can use it as a go, no go type of measurement. You can see here in the report, we've got a couple of different types of outputs. It's kind of hard to see because the picture is a little small. But at the bottom there, you can see true position outputs. The true position outputs are related to what we call 2D target charts. So the 2D target charts are a very easy way for you to see whether you're in or out of tolerance and where that actual feature is falling within the acceptable range. On top of true position, we offer every other GD&T type of calculation, whether it be profile, angularity, perpendicularity, parallelism, true position, composite true position, all of the usual suspects, and all are compliant to ISO and ANSI methods. As I was saying before, you've got customizable report options, so you can really kind of set it up yourself, and also various report types. So let's say, for example, it's advantageous for you to get your report printed out as a PDF. Okay? That's fine. You can set the system up. You can set up the program in such a way that once the program is done running, the report is generated, the operator has either looked at it or maybe it's not their responsibility to look at it. That's okay. That report can be saved anywhere it needs to be saved. It can be dumped to a server, anything like that, all automatically, completely transparent to the operator. So really all the operator is doing is calling up the cycle like any other cycle that they're used to and hitting cycle start and waiting for the machine to finish its task. Now, along with that, you can also obviously be programmed in so that it could be part of a process where it's not being called up by a human, it's just being activated by a cutting cycle or another cycle or something like that. On top of that, the reporting data can also be dumped into SQL databases. So if your company uses some type of SQL database to manage all the metrology data coming off of the, let's call them typical metrology devices, we can feed right into that system. And once again, it's all totally transparent to the operator. And it really comes down to how the system is programmed. So the programs can be written and generated in such a way that the operator really doesn't have to do. Okay, so that's kind of just an overview of the software and all the different ways that we could use it, different methods and things like that. So now I've got a couple more slides here that we're going to talk about, and these slides just kind of go through a couple of case studies or some situations that we've used the software to kind of talk about some different environments. So the first example that we have here is what we're calling high mix, low volume machining. In this case, we had a fully automated cell. The fully automated cell was, the rough stock was loaded by a robot into the machine. This is a mill turn. In that case, once the robot loaded the part, we did a probing cycle to roughly locate some information about the part. Obviously, it being a mill turn machine, there wasn't a lot that we had to do to adjust it, but we would check depth and things like that so that we knew where to start the program and update the work offset to. So the robot would drop off the stock. We'd come in and probe a cycle. And in that case, once the probing cycle was good and everything was happy, then the cutting would commence. So throughout the process of cutting the part, we would probe key features along the way throughout the different operations. Information was fed back in to determine pass fail, to update tooling offsets and things like that. Once the part was completely finished on the left-hand side or the left-hand spindle, we did a final inspection on that, on all the details that were machined there. The robot then grabbed it from the left side, moved it over to the right side. All the details for that right side spindle were machined. The same process would happen, probing, cutting, with a final pass on the probe to determine pass fail. If everything was passed, then the robot would grab the part and put it where it needed to go so that it could move on to its next phase of existence. Once we were done, the data from the two programs were merged into one report, and then the report was saved wherever it needed to be saved. So this is a situation here And when you look at cut, measure, cut processes, or incorporating any type of probing into a manufacturing process, you want to kind of think about, who do we want to manage the system? Who do we want to be the master in this situation? Who do we want to be, controlling the strings, for lack of a better term? So in this one here, in this example here, the cutting cycle, actually the automation cycle, was in charge of managing everything. So the automation cycle would load the part, the cutting cycle would do its job, the probing cycle would do its job, the probing cycle would feed back to the cutting cycle, and everything was managed from that automation cycle. Okay, so, and all that was done, and once we were done, we'd start over again on the next part. Another example that we have is adaptive tool compensation here. So this was in process adaptive tool compensation. In this application, we kind of flipped the script and we let the probing system, or the probing cycle, kind of do the management of everything. So the measurement cycle kind of kicked everything off. It managed the entire process. And this was a multi-cavity tool, or multi-cavity mold. Okay. So every time we would go in and produce or manufacture or machine one of the cavities, the system would then immediately switch to the probe. It would probe some key features on there, and then determinations were made to either update tool offset, or this project here also included sister tooling. So if a tool did get to an end of life situation, then we would automatically load the sister tool for that tool, and then continue on with the process. Another step of the process that was also included was the work offsetting. So in this case, what we would do is, when we got into the area, because the parts, I believe, I don't remember that much about this project, but I believe there was something about the cavities being, I don't know if they were cast or something, but basically what we would do is we had a typical location of where the part should be, or where that cavity should be. And before we did anything, we would go in and probe it first, and then make fine adjustments to the work offset based on, whether there was too much material or a little material or whatever on the cavity, and then make those decisions, make those corrections, do the machining, and then do the probing as well. So in this situation, we had, once again, the probing system, or the probing cycle, driving the entire process. But once again, it was the same concept, where we were applying measure, cut, measure throughout the process to update work offsets, update tool offsets, and really overall improve the process capability. So just one more comment I want to make about this on the improved process capability is that I'm sure any of you that are using cut, measure, cut processes understand the importance of them, and understand that what they can do for you. But if you don't, I'm just going to tell a quick little story. So we had a customer that had some very tight tolerance features, and they were having difficulties managing process capability throughout the process of machining these parts. And they were, using, let's call it, traditional methods. They weren't doing any probing or anything, in the program to do anything, adjustment or anything like that. And they were averaging, on a couple of their key features, they were averaging, less than 1 on their CPKs for the process capabilities. Once they incorporated a cut, measure, cut loop into their machining process, they were able to bring those CPKs above 5. So and we can obviously, if you have more questions or anything, we can kind of talk about this. But that just kind of goes to show you what this process can actually do for you. So by actually updating the part position, or updating a tool offset or something like that, you can vastly improve process capability on your part without really adding a lot of complexity from the operator standpoint. They're just kind of standing there watching the machine, managing it, making sure everything's okay, but they're not having to do a lot of gyrations or anything to make sure that the part's going to be made better. So one last slide here to just kind of talk about our ecosystem. So our CappsNC software is our on-machine metrology software. So we've got a bunch of different variations, a bunch of different tools built into that software. For example, we can do non-contact scanning, laser scanning in the machine, as well as probing. Licensing for the software can be done in different ways. So there's a myriad of ways that all this can be managed through the software. I'm not going to get into all that right now because that's not the point here. The point is that what we're looking at here is a software that brings all the functionality and all the tools of a full CMM software out to the machine and gives you that flexibility. So on and say thank you to everyone for attending. I hope we taught you something today. And I will go to our last slide here and just say if anybody has any questions at this time, let's we can go ahead and discuss them.
So Chris, I had a question right off the bat on your story. So just for the audience, you said that the customer was running what type of CPK before you started the process?
Their CPK was less than 1, so so really they weren't process capable at that point. Really, if you go by the standard 1.33, cutoff.
So just for layman's terms, can you just kind of describe what for the audience what a traditional CPK was going to offer you, like what that terminology means to the manufacturing world? Like if you're under a 1, what does that mean to your part quality for your manufacturing? So what would you do in a typical CPK? What is a CPK? What when it happens when you take it from under 1 to 5, what are you getting?
All right, that's a good question, Dan. So it's been a while since I've been in the quality room, but I will take my best shot at it. Anybody on the call that catches anything I do wrong, please don't take it personally. So what we're looking at, when you look at process capability, what you look at is what amount of variation in your part data is due to the capability of the process. In other words, how reliably can I produce a part consistently, right? How, if I'm going to circular interpolate a hole or whatever, how consistently can I hit that target and get that size and get that position, right? So when you look at a standard CPK analysis, what you do is you take all of your data and you put it under a like a 6 Sigma chart, right? So a bell curve, right? And what the process capability is telling you is under that curve, you've got to maintain your variation of your process from all your parts. So typically a capability study is a 30-piece capability study. You will take 30 random parts, you will probe some geometry or some characteristic of the part, and you will put all that information into a CPK calculating software, an SPC software, and based on the variation of all those measurements, it will plot that data under the curve, essentially. So now, a lot of times people think, well, and if anybody's ever heard the term like 6 Sigma, for example, so the center line of that curve, wherever the top point of that bell curve is your, let's call it part nominal or part 0. Now, as you move out, and this is all based on tolerance and percentage of tolerance and everything, as you move away from that peak of the bell curve, those are sigmas, right? So if you say 1 sigma, right, then it's like in that first range close to the nominal, right? And then as you spread out from there and the curve comes down, you go out to more sigmas, right? So while your process might be, you might not be, how do I want to say this? Let's say that you're producing parts and you're really concerned about the size of a hole, the diameter. Now, the process could be capable if you have a tight variation. In other words, you don't have much variation between your part measurements, but what if they're all, I don't know, 20% off? So 20% of your tolerance. So let's say your tolerance is plus or minus, 5 thou. And let's say that every single one of your measurements are hovering right around 2 thou, but they're all varying less than 5/10. Okay. That is a very good process capability. Okay. It's not necessarily at nominal, but it's very tight to what it is. And oftentimes people relate bow and arrow shooting or target shooting to capability studies. So you might have a tight grouping, but the object is to have a tight grouping at the bullseye. But if you have a tight grouping and it's off the bullseye, but still on the dartboard or still on the target, you're doing okay. So basically what was happening and what would give you a small CPK is that the data is spread out all over the place, or it's tight, but it's at one end of your tolerance. So by going in and setting up a probing process where they updated a work offset, they were able to fine tune the work offset to a datum, the most important datum to the feature that they were machining. And by doing that, because they weren't holding the part consistently, so they would go in and make the datum feature, and then they would zero on that datum feature. And by zeroing on that datum feature, that meant that when they machined the feature that was supposed to be measured relative to that datum feature, they hit the target very closely. But again, because they were controlling the work offset, shifting the work offset to that datum every time where it was.
That was a good answer, Chris. And would you say if when you get to a capability study that's above 2 CPK, you're pretty much bullseye, right?
I would say I would be pretty happy with that. Yes. Yeah.
So five is you're splitting arrows.
Oh, it was amazing. It was amazing. In fact, the gentleman that we worked with, he was, I believe he was a data scientist. He wasn't even really like the quality manager or anything. He's like, I had to run it like 6 times because I couldn't believe the numbers that I was getting. So.
Perfect. We have some other questions here that came through the chat.
Okay.
One of them is how do the kinematic probes work when you rotate 90 degrees from example? How does the gravity affect the measurement? Does CappsNC compensate for that?
Oh, that's a very good question. Well, in the case of a table machine, obviously that there's no issue there, right? Because the head is not moving. So the way that we manage it from a perspective, if you're on like a mill turn or a head table machine or a head machine, is that when you orient the probe to a given orientation, we calibrate in that orientation. So if there is sag due to the probe, let's say you've got a long stylus on it or something like that. If there's sag in the probe, that sag will come out in the calibration as X or Y, let's call it run out for lack of a better term, but X or Y deviation in that given axis. Now, when you go to probe at that axis, so you calibrate it, and when you calibrate, you can see quality of calibration, just like you do on a CMM. When you go to use that angle to probe a feature, that calibration is automatically applied to that measurement so that it should effectively apply the XY variation. Therefore, it should include the droop into the calculations.
Perfect. We have another one here. It says, many new CMMs have the ability to scan features of high density data. Are there new advancements that will allow this type of measurement on CNC machines?
Actually, yes. So about, I don't know, a few years ago, Renishaw actually initially released, and now they're starting to put it more into market, the Sprint Pro. So if anybody on the webinar here is familiar with analog scanning, like Renishaw, SP25 scanning, or like on Zeiss, you have the Vast head, or with Renishaw, the SP80 head. Those are constant touch analog scanning probes. Well, Renishaw has developed a probe to do that right in the machine environment. It's called the Sprint probe. And the CappsNC software does have an interface to manage the data coming from that probe. So we do have that built into our interface. You can you can generate scan paths in our environment. You can post the necessary G code for it, and you can run it on the machine.
Perfect. I don't think we have answered that question. I had another question here. What is needed to install this? So let's say I have a 5-axis machine or I have a 3-axis machine. What right off the bat I need from the machine tool builder, and then what do I need from you guys?
Okay. Good question. So essentially what you need is the controller obviously needs to be one of the 3. The 840D is the one I'm most familiar with, so I'll apologize for not knowing the other 2. But a controller with OPC, let's say that, right? The license option that you pointed out during your part of the presentation, Dan, That is necessary to allow us that connection through that. We also need to be able to plug in to the network of the machine, the controller network, not necessarily like the company network or anything like that, but we need to be able to connect Ethernet cable to the into the controller network. A PC needs to be connected. Now, the PC doesn't need to reside directly next to the machine as long as the PC is networked into the machine, into that controller network. We can manage that. Other than that, not really much. I mean, you need a probe, obviously. And once again, as John said during his part of the presentation, we're kind of to make a joke here, we're kind of the Switzerland. We're kind of Switzerland. Doesn't matter to us who we work with. A skip signal is a skip signal. So as long as we understand what kind of probe you need, so that we know, okay, yeah, we need to do a kinematic calibration or a strain gauge calibration, we're all good. To just kind of give you an overview, we load a handful of macros on the controller, and those macros manage all of our movement, all of our data management, and all of that. So yeah, that's about it.
Another question here. What is the learning curve of the software compared to just like probing apart? Like, what have you had some data on the learning curve?
That's a great question. And it's I don't know. I guess if you want me to give you the salesy answer, it's difficult to say because different people learn at different rates. However, I might be a little biased because I've run the software for over 20 years. But I'm going to actually pass the mic over to John real quick because John's been with us for about a year now, and he had not run our software beforehand. So I'm going to let him give his little bit of perspective on this.
All right. So to address the question of how hard is it to learn, is there a learning curve? I'm familiar with SolidWorks, CamWorks. That was the main gaming software that I used, as well as I did end up messing with the Spree and learning Siemens NX as well for various programming, whether it's mill turns or milling machines in general. When I first loaded into CappsNC and started getting the lay of the land, so to speak, it's very simple to get going on it. Some of the more intricate features took me a little bit of time to kind of learn, but overall, it took me less time to pick up CappsNC than it ever would have taken me to learn SolidWorks or Siemens NX. It's fairly intuitive. Now, when you get into reporting, that stuff gets a little different. I am a CNC programmer, so I have no background in the quality department in making those reports. So that was definitely a learning curve for me. But it was more of a learning curve for me because there's so many options that it makes it hard to really narrow it down to exactly what you want your report to look like. But overall, I would say the learning curve on CappsNC is very minimal in comparison to learning a CAD/CAM software.
Perfect.
Yeah, and I'll just add a caveat to that, Dan. As John said, from an NC programmer's perspective, the movement will probably be fairly easy to pick up. However, because there is sometimes an art to making reports and getting the information that you need, that there can be a learning curve to that.
So another question here. Do you offer a standalone solution if it cannot be networked to the machine?
We do. So we do offer an option. We call it the file interface. And in that situation, you can generate the program in an offline environment in engineering, for example. When the machine runs, or when the program runs, sorry, all the recorded data is dumped into a points file or a file on the controller. And then that file can be pulled off the controller and then brought into the programming environment and what we call processed through the program to generate the reports. The one thing I will say about that is that if you're going to look at the system in that way, is that you are limited in your functionality. In other words, it would be a cumbersome process to do a work offset update in that case, because you'd be, posting the program, getting the data, reposting the program, moving it over. So there would be, there's a bit to it. But if you wanted to just do some inspection on the machine, I think that would be a viable solution. So, yes.
So we got another one here. Sorry. So someone It says, can you give an approximate cost of to tool up one machine or multiple machines? Seems like a broad question.
It is. So I'll give a broad answer. So depending on number of axes, complexity of machine, and things like that, the software can range anywhere between, let's say, 35 to 70,000, depending on the functions. Obviously, 70,000 is going to be, you know, a multi-axis machine with, you know, all the capability and everything else. From a multi-machine perspective, part of our licensing is what we call, we break it up into what we call programming and execution stations. So, and that can also be done off of a site license. So if you had a site license or a server license, you can say, okay, I've got 5 programmers, but only 2 of them are ever going to be programming at one time. All 5 could be connected to a licensed server. You have 2 active licenses that can be used concurrently. So you can save money that way. So you're not buying 5 full seats of the software at that point. You're buying access to 2, so that you could have 2 running at the same time. And then also splitting out the programming station from the execution station is also going to be a cost savings as well, because not only can you license the execution modules in the same way, but you can also add execution stations independently or add programming stations independently without having to pay the full cost of the software. The only thing I'll say about the execution stations is that in a production environment, if you went with a license, a server license solution, and you say, okay, you know, I've got 5 machines, only 2 are ever going to probe at the same time. You could get yourself into a situation where one machine is waiting for a license. So a lot of our customers do not manage execution stations in that way, but it is possible to
do it. Perfect. Then we have one here. Do you support older versions of the 840D, like HMI Advanced Powerline? What limitations do you have with older versions, i.e. IO feedback?
That is a great question. I just finished a project on a big trim and drill machine that had a power line controller. So we do have the ability to connect to older controllers. If it's a question, if it's a very old controller and it's a question, let us know, and we'll probably reach out to Dan and ask him what his opinion is on it. Obviously, there's some functions that we can look at in the controller or licenses to make sure that, you know, if they're not there at all, then, maybe we might say no. But we do have the ability, and we also have the ability to talk to, no matter what the operating system is in the background of the HMI. So if the HMI background is Linux, we can still talk to it. If it's, XP, we can talk to it. 7, we can talk to it. So the 840D power line and solution line are the only 2, let's say the solution, the power line, it would be the oldest control that I've worked
with. And then says, can you show an example of setting up a probe and operation in your software? That was one of the questions that came through.
I mean, I think at this point, I'm kind of not set up to do that right now. I mean, it would be minutes of not fumbling, but minutes of getting a program open and started and things like that. But if it's something that somebody wants to see, we could absolutely set up a separate call, like a WebEx or a Teams call or something, to kind of walk them through it.
Perfect. Yeah. So whoever asked that question, if you wanted to reach out to either me or Chris or John on this webinar, shoot me it. I did post our email addresses in the document. If not, this will be on our YouTube channel, and you can always get us there as far as reaching us. So
yeah, but just from a let's call it a imagination perspective, I guess. So the way that we build our probes, we have a head model. That head model starts with the shank. You pick the shank from a list. You pick the probe body from the list, and then you pick whatever style-eye components that would attach to that. basically using pictures. So you would click on an image, it would show up in the software. You could say, oh, that's not what I'm looking for. If you have the part number for Runnershaw, you can do that. But the library that we have of probes, we have boom probes, we have the whole entire Runnershaw library, and we have some Marpost probes built into our library as well. So it's pretty much a drop and drag kind of thing.
So, you know, one thought from my side, if you guys are interested, as maybe a continuation to this event, why don't we look at incorporating the software on our DMU50, and we'll do a YouTube live, and we can run the software and do like a full live demo.
I think that's a great idea.
Good. So we can have a takeaway. I'm sure the audience would probably get some interest in that. From my side, thanks guys for jumping in. Great job. Great job, Dan, as well. I'm seeing the event. It was a lot of good content, and certainly interested in seeing what else we can do.
Yeah,
Well,
thank you, Chris. Thank you, John.
Yeah. So yes, from everyone at AAT, AT3D, Chris and Dan, thank you very much for the opportunity. Really enjoyed it. Thanks.
Appreciate it. Thank you.
Okay. All right.
All right, perfect, guys. Well, I guess with that being said, thanks everybody for joining us. Dan mentioned the video is going to go on our site, as well as we'll certainly send you out the link today after the event, and we look forward to seeing everybody next time. So again, thanks Dan, thanks Chris, and everybody from AAT3D, and we'll talk soon.
Okay.
Yep,
Thank you all
everyone.
very much. Bye.
All right, bye-bye.